Hi, welcome back. After the last video where I explained the functionality of this oscillography, I would like to present some new features that I've added to this tool that you will be able to find on the right-hand side at the bottom, where you can find a list of different variables that influence the shape of the waveforms. You will see the nominal voltage, the Rx, which basically represents the impedance of the line, the resistive and reactance part of the impedance. The RS and XS represents the source impedance, so just behind the relay. The POW is basically the point on wave, the moment where the fault occurs on the wave. R load is the load prior to the fault. So here I set it to 100 ohms. And so if I make a change, for example, on the X value of the impedance, that will change the X over R ratio and the rate of decay of the waveform. So here, for example, if I just increase it to 20, you can see that it changes the way the wave behaves. Okay, obviously, the more I increase X, the impedance increase, so the voltage drop decrease as well. So the point on wave, when I just use as well, you can see how it just influences the waveform. So the load as well, you can see that it changes. Obviously, when the load is, the greater the load, the greater the voltage drop will be. So you can see as well as here I've got the K factor, which represents the percentage where the fault occurs on the line. So here is at the end of the line. So by decreasing this value, you can see that obviously the closer the fault occurs, the bigger the voltage drop occurs, as you can see here. So I'm just going to refresh this page here. So yeah, this is web-based, so you can just refresh and start over. Obviously, later on, I will find a way to store this on the locally on a file, and optimally, that's where I'm aiming to get at, is to be able to import COMTRADE files, which is basically 2 files or 3 files, depending on what you get, but which is the DAT file where the data is, and the CFG, which is the configuration, where how many analogs and digitals are included in the file. So that would be a very good thing to implement on this tool. So here is another element that I've implemented here, which is called the display Z or display Z, depending on where you're speaking your English from. So when you click on this, you will see that it brings you to another page where the impedance calculated from the relay standpoint is shown. I don't know whether many of you have seen this before, but here, this dot here that you can see there is the load impedance prior to the fault. As soon as the fault occurs, obviously the impedance decreases, but you can see that this is just circling around just to finally get to the final point. Many might think that from the load you'd go directly onto the fault condition, but that's not the case, because if you look at the equations, you've got obviously the exponential j omega t, which is decreasing by the tau value, which depends on the X over R ratio. So that's why you've got this circling around. So you can, you can do things like decreasing the fault location. Let's put it at 31. So when you update this simulation, you can see that you will end up at 30% of the line, and the impedance here is at 3.1 at 84 degrees. So let's put it back to 100. You'll see that, for example, the line here has a R which is much smaller than the reactance, about a 10x ratio. So if I just change this R, let's put it at 6, when you update, you can see that now the resistive part of that line is greater, which might not be something that you'd observe in practice for an overhead line. So this is what I've implemented. I just wanted to show this, and I would welcome your feedback, and you can leave your comments here on the top hand corner. You will be able to leave a comment on my GitHub repository. So looking forward to have your feedback, and let me know in the comments what you think. Later.